Okay, so lastly, I would like to go over one more very common black box optimizer, which is the Gaussian processes. This is a very good tool to use when your sample costs are very expensive. It provides us with some interesting mathematical guarantees. So this was originally, I guess, developed for a gold mining company by a South African mining engineer back in the 60s. His name was Daniel Craig. So this actually, Gaussian processes is also known as Craiging, I don't know, after his name. So the original problem was to find, we wanted to find the point on some map that is richest in gold in some physical environment, right? Sampling the soil is very expensive. You have to go there and dig deep in order to sample how much gold there is there. So what we'd like to do is, given the current samples that we already have, we would like to decide where should we next sample, where should the next sample be taken from, because the samples are very expensive, right? So if these are our three samples, right, so we have a lot of gold here, we sensed a lot of gold in this location, less amount here and not a lot in this location. Where should we dig next? Probably somewhere around this point, I'm guessing, right? Okay, this is just the intuitive process, right? Let's see how to do it more mathematically. So in order to provide an answer for this optimization problem, we need to define the multivariate normal distribution, and then also how to define some conditional distributions within a larger multivariate distribution. So for instance, if we have this two-dimensional multivariate normal distribution, I can ask what is the distribution over y, over one of these dimensions, if x is known to equal to 2, right? So this is our two-dimensional Gaussian, and we'd just like to slice it in a specific space. So the high-dimensional Gaussian is defined. How can I compute a Gaussian given a value to one of these dimensions? Any idea? It's not very simple, but you can derive it. Specifically, it's theorem 4.3.1 in this book. We won't prove it. But for the general case is that you have a lot of dimension and you would like to compute a sub-multivariate distribution from some sub-fixture of some of the dimensions. Some of the dimensions are fixed. In that case, you can define this sub-multivariate distribution given some fixed dimensions, where you set the mu vector, the mean vector, as follows: mu x plus mu x is just the mean of all of the x parameters. These are the parameters that you would like to compute the multivariate with respect to. And then plus the covariance matrix of x and y together times the inverse of the covariance matrix of y with itself. And of course, this is not necessarily a single value because, well, y can be a vector of set values, multiplied by y minus mu of y. Okay, which is, again, this can be vectors. And you can also define the covariance matrix of x, what you'd like to compute for, with respect to some fixed y's, as follows. Okay, we won't prove that. So it was a bit of a trick question. I mean, it's not a straightforward answer, but this is the answer. Okay? So, for instance, if we're given a two-dimensional Gaussian here, we, for instance, can compute mu of x given some y, right? Depending what y is, but we can simply plug in these values and we'll get the mu vector. In our case, x is just one dimension, so it will be just one value. And we can compute it will be a matrix, it's just the variance value of x given y. Okay, so how can we use this understanding to do some prediction regarding the mean, what's the mean value of gold. So to compute the distribution of gold in a new location, the mean and the variance. So we have several known points where we already looked for gold, right? These are x1, x2, and x3. And we would like to predict the distribution of gold, the amount of gold, in a new point. Let's call it x star. We'd like to compute the mean and variance. Of course, there is a specific value in x star, but we don't know it. We'd like to somehow approximate the normal distribution around x star that will tell us the probability of finding gold and how much gold in that location. The key idea here is to find is that if xi and xj, if 2 points in our space are similar, close to each other, then we expect the output of the function at those points to be similar too, right? I mean, if I'll dig a hole next to, well, a previous hole that I know how much gold is there, then I'll say, well, I know it should have about the same amount of gold, maybe with some extra variance. Makes sense. But we'll also need to define what is close. I mean, if you're just going out digging for gold, then close makes sense, it's just the distance. But that's not always the case. Commonly what we do is we use what's called a kernel function that defines the similarity, or what's the distance between each point. And that can be very different in different spaces. And this is done through what's called a kernel function. Kernel function defines the covariance between 2 points in some user-defined space. The chosen space should fit the approximated function, or the domain that we're trying to approximate the function in. For instance, one very common kernel function is known as the squared exponential kernel, provided here. It has some deeper theoretical meaning which we won't go to. You can just notice that if the distance between 2 points tends towards infinity, then the kernel value, the covariance between them, will be. However, if 2 points are very close to each other, 2 samples, very close, that is the distance, the norm distance, the L2 norm between them tends to 0, then the kernel, the squared exponential kernel, will be 1. So now we would like to do some Gaussian prediction regarding the new point. Okay, so let's assume that all of our current points, x1, x2, and x3, come from some multi-Gaussian process, multivariate Gaussian process with 3 dimensions, or 3 observations. And we'll assume that our new point that we're trying to evaluate, x star, there is some underlying normal distribution that defines it with some u and some variance. You can look at it as covariance with itself, just the variance of x star. That location, of course, we can generalize it to several x stars. Right, this is why I'm giving the general covariance notation. So kx x star, so the kernel function of x star from itself equals 1, but that's not very helpful. So we just say very high variance between it and itself, and some u defined by the, well, whatever the underlying mu is. We'll have to somehow compute it or define it. So this might not be very useful, or I mean, we have to somehow define this new normal distribution around our new point. Or, again, we can generalize it to several points. The way to do that is to assume that f, our previous points, and f star, our new point, or new points, are jointly Gaussian. Okay, they are Gaussian altogether. So in this higher dimensional Gaussian, we know some of the values, right? For instance, we know the mu values affiliated with this f. We don't know that one affiliated with f star. We know the covariance matrix affiliated with f. But we don't know all of these values that are affiliated with f star. So the question is, how can we determine the mean and variance for f star? Any idea? So this is where we go back to the beginning and we'll use the posterior conditional of a multivariate normal distribution that we defined initially, right? These two equations. And now we can compute the expected value of f star, or the mean of f, given all of the known points, the f points, as this value here, just following this equation. And we can do the same with the covariance matrix following this equation. Okay, and this will give us a much more reasonable assumption regarding the distribution of the new point, right? Give us some Gaussian around the new point that is based on all of the known point values, the mean of those values, and also the covariance of those values defined by the kernel function, as defined by the kernel function. When are such Bayesian optimization tools useful? As I said in the beginning, they are very useful when f, our objective function, is very expensive to evaluate. It's very expensive for us to collect samples. For instance, when we need to simulate a day's traffic, that can be very expensive. If we need to somehow do some car crash outcomes study, right? These are expensive. We'll crash our car, drill a hole in the ground, looking for oil, looking for gold. If we're using human subjects, these are also considered very expensive. Or if we simply have a bounded number of samples provided to us and we can't go over our budget. It is also very useful when f is continuous, because it will allow you to, specifically if you have a good correct kernel function, a well-fitting kernel function, it will allow you to do a good inference in a continuous space. It's also useful when f lacks known special structure like convexity or linearity, right? Because it, as long as f does follow the assumption of being normally distribution, fitting a Gaussian. Which, by the way, in many natural cases, real-world cases, this is fitting a Gaussian is powerful. It's a good guess, let's say, in many cases. And again, Bayesian optimization, like any black box optimization, can be applied without knowing first. It does require first order derivative, and of course, does it also require a second order derivative. And it can be useful when we require to converge on a global optimum. Okay, so I'll just do this. So, how do we perform optimization using Bayesian optimization, using Gaussian processes? So, we do it as before in iterations, and each iteration we obtain the best sample candidate from some acquisition function. We'll discuss this later. So we're going to look at our current points that we already sampled, and we'll try to guess the next best sample to evaluate in the real world. We sample the objective function at that point, and we update the Gaussian process according to the new data point, and we repeat the process. Okay, so we obtain the new point, and we update our Gaussian process, and continue to the next iteration for choosing the next point. And we do it iteratively.